Okay, continuing. So what's stronger? Negative 0.9 or 0.7? Negative 0.9 is stronger. So again, that negative doesn't matter. It's just what's farther away from 0. So that's what we got. So we're looking right there. Any questions about that? So that's like part 1. So part 1 of today's lesson is just correlation coefficient, and can we determine what's stronger than the other piece? Part 2 is we're going to take some data, and excuse me, you actually did this in chapter 1. You used Desmos, you made a linear regression, and then you did all those fun things. Well, we don't really have all that much time because we're a 2-month class, so I want to make sure you have time to actually try it. So I just pulled Desmos up, and what we're going to do is we are going to compare age and height. Okay? And so we're going to come up with the formula that Desmos is going to give us. And then from there, we're going to answer some questions. So what you would do, you would start just by going into Desmos and putting the data into the table. And so I have that data there. I'm going to delete this so you can see where it comes from. So the data is already in the table. But like I said, on your homework, you're going to have to put data in the table. How do I get a table to show up in Desmos? Yeah, so I hit plus up here, and then table drops right there. Or, honestly, you can actually just type in the word table and it pops up. That's what I do. But either way. So then I put my data in. Did that really fast. Now, you notice on Desmos when you do that, that these 2 dots and a line and 2 more dots show up. And if you just click that, it gives you everything you need to know. You should feel pretty lucky because this is the first year Desmos actually did that. Before, it would give you like this big column of all these things, and then it would make the kids like go through and solve it all. Technology saved you a little bit of pain. So the formula, I wrote it on the board because it gives it to you. It's right there on the whiteboard. So that's what we're going to write down for our line of best fit for the predicted height. So I'm going to write this down, and let's do some rounding here. I don't really want to write all of that 28.97556 down. So let's write 28.98. Okay, that can be our starting amount. And I'll come back to that in a moment. And then my slope I'm going to write as 2.65x. Any questions about why I wrote it that way? It's got to be one. How do you write your lines? Do you write your slope and then your y-intercept, or y-intercept and then your slope? I've done this for years. You do your slope and then your y-intercept. But right there, I did my y-intercept and then my slope. So the question is, Nichols, what the heck? Well, here's what the heck. In stats, we want to know, where does my data start? That's the first thing that I want to see. So I write my y-intercept first. Then I want to know, how is my data changing? So that's where the slope comes in. So in stats, if you take AP Stats next year, they will write their lines like this. If on the test, you write your line as 2.65x plus 28.98, I'm not going to take points off. Okay? But you need to realize if you go into stats, they are going to get picky on stuff like this. So I'm going to slide down here. And where did the data start? It starts at 28.98. That's just inches. So the data starts when someone's 2 years old. This girl, whoever it was, that was their data point. And then how does it change? It changes by 2.65 inches per year. Now, I'm not picky about how you write the line, if you do the y-intercept and then the slope or vice versa. But I do get picky about the data, how we talk about it. If they give you units, you have to use units. You are interpreting the context of what the numbers are. Okay, that's a big part of stats. So I want to make sure that you are writing that stuff down. Any questions so far? We haven't really done anything. We've just copied and pasted stuff in Desmos. Desmos did all the work. So anything at all, though? Okay. First question says, using the regression, make a height prediction for a girl that is 7 years old. So I just go 28.98 plus 2.65, and then I put 7 in for x. And, you know, if you're not sure, like, does 7 go in for x or does it go in for y, look at your table. Your table, good. Your table has age in the first column. That's 99% of the time your x column. So there's something to be said for that. So everybody should have a calculator right now. If you don't, go get one. Grab one out, type it in. I almost yelled at you and you have one sitting right there. Good question. We're going to talk about that. It doesn't. But that is a good question. So we're going to type this in, and what'd you get, Simon? Me? Yep. 47.53. Anyone else get that number? Okay, so we got the number. That's good. Now, here's the deal. We also got to think, does this make sense? Because we have a bunch of data to tell us does it make sense or not. So I'm going to look at this, and 7 years old, I look, oh my gosh, never felt so old in my life. Okay. And then, there we go. If I look at my data table, 7 years old, they collected data for a 7-year-old to be 48 inches tall. My answer of 47 point whatever it was seems relatively close and reasonable, so that's a good thing. The first class gave me an answer of 21, and some kids were just like, I don't know about that. And then some were like, the one person was very vocal about it, so I was like, okay. So we decided as a class to move on. And I will let you make mistakes. Those of you who had me first semester know that. So we went forward a little bit, and then finally someone was just like, if we started at 28 inches tall, how did we get shorter? I guarantee you that on this test, I will ask you a question based off data. And we do this with money or other things. And it will be like, how much money are you going to have if your bank account grows by this amount? Someone will be like, you're going to have $7 billion in 2 years. Pump the brakes there a little bit. Let's think about how realistic that is. So you want to think about, is my answer good? And in this case, yes, it's reasonable. Now, I'm going to call you out. Kate actually asked, doesn't this number just give me what the data table tells me? And it doesn't. What Desmos is doing is it takes your scatter plot, and so I'm going to put a bunch of dots here, and it draws this line. And so what it's doing is it measures the distance from that line to that dot, this dot to that dot, and so on and so forth. And what it's doing is it is turning that line back and forth to minimize those distances until it can't minimize it anymore. That's the line of best fit. So this is not going to give us a data point. It will give us something else, okay? So that's a good answer. Now, we're going to do the next one, but I'm going to change this from 30 to 50. Let's calculate that. So I'm going to have 28.98 again, plus 2.65 times 50. $161.48. And you know what? I do want you to divide this by 12. And we get 13.4 something. How many 13-footers do you see walking around?
Are walking? Not many dead.
I'm gonna move past that. So that is pretty tall. It's approximately 13 feet something. No. So here's the deal. If you look at the data set And this is actually very simple. If I look at my data set, I'm going to look for the lowest number and the highest number in my X column. And so I go from 2 till 10. Extrapolation is the death of your data. We do not extrapolate, okay? So when you extrapolate, really bad things happen. Now we can kind of think about, some of us might be done getting any taller. Some of us are going to be done getting taller in like 5 years. But you don't continue to grow taller every single year. So our model has limitations. Our model starts at 2 and it stops about 10. Okay? Now, if you asked, well, can I plug in for 11? Can I plug in for 12? Yes. There's a gray area. We don't get into that gray area. If we give you a number, we're going to make it painfully obvious that it either works or it doesn't. So the question down below, it says which is an appropriate prediction and which is inappropriate. We're just going to answer the inappropriate one. So if you're 50 years old, 50 years old would be inappropriate because it is too far outside of our data set. It honestly comes down to the one simple thing at the end. It's outside our data set. That's really it. So we don't give you that gray area to look at. In statistics, if you take AP Stats, you would look at that, and you would find where that gray area actually ends, and it's just black and white, and it's either it works or it doesn't work. But again, we don't get into that, but we will test your knowledge. We will give you numbers in the data set, and we'll give you numbers way the heck outside. And then you have to interpret the answer and deem, is a 13-foot individual walking around a plausible answer? Last thing then, what is the correlation coefficient? And that actually comes from Desmos. And so Desmos tells you right here, it gives you R squared, which is something you will find out about later. And then it gives you R, which is what our correlation coefficient is. So R is just 0.996. And so that is a very strong correlation. What questions do we have? All right. Okay, if you go to your 7-3 homework, skip the first page. You have to do the first page, but it's multiple choice. It will take you 1 minute. But what I'd rather have you do is get your Chromebooks out, do Desmos, so I can help you with Desmos, so you can be done with it and not have to worry about it. And so if you want to work in pairs, that is fine. But start with the Desmos piece, get it done with, and you can go back. Was anyone gone yesterday? Does everyone have that white sheet for 7-2 that is the homework picked up? Good? All right. Time is yours. Let me know if you got questions.